All right, good afternoon, everyone. So a student just told me that there's only one question on the quiz on Friday, so that's a mistake. Please don't take it yet. I'll fix it, and then if you did take it, then I'll try to, I don't know, I'll do something where you can take it again. Okay. So let's, so how was the midterm? Is it hard or okay? All right.
Just enough time.
Just enough time? That's what I was hoping for. Yeah.
Do you know when we'll get those back?
I didn't get them myself until today, so I'm going to try to grade them by the end of the week, but it always takes me a while, so my goal is by Friday. Okay. All right, so let's remember where we were. From last time, we were talking about the gradient. So basically, we're always dealing with a scalar valued function, and when we take the gradient of that function with respect to some variable that could be vector valued or matrix valued, we just get something that's the size of the original variable, where we have all the partial derivatives of the original function with respect to the elements of that variable. So this is the vector case, this is the matrix case. And let's see, so with that, one of the things we talked about was first order approximation or linear approximation. So in the scalar case, it looks like this. We have some nonlinear function, and we want to approximate it by a line at some point. We can obviously do that in the linear case, and we get this expression here. We have the approximation is going to use the value of the function at the reference point plus the slope at the reference point times the deviation from the reference point. So that's the case where we have scalar inputs. Then we can redo this for vector inputs, and we find we have something similar. We have the function at W is approximately equal to the function at the reference plus the inner product between the gradient at the reference and the deviation from the reference. And we saw that the same expression held even in the matrix case. So again, we have the inner product. And in this case, though, the inner product is defined differently than when we have vectors. But if you look at the definition based on the inner product, it becomes the same. Okay, so then one of the ways that we can use this linear approximation is we proved that the norm of the gradient is the maximum slope. If you are sitting at a certain point in the function and you look in every direction and you see what is the maximum slope, it ends up being the norm of the gradient vector. And if you say what is the direction you have to travel in to get that maximum slope, then that is the direction of the gradient vector. So in other words, gradient vector tells you which direction to move for the function to maximally increase, as well as how steep it's going to be, what the slope will be if you move in that direction. I think that's a good review of where we were. So then we were working through some examples. So let's look at this matrix valued example where we have function j of a matrix W, and we're going to make a pretty simple function of it that will allow us to go through and apply some of these things we learned without causing too much of a headache. Okay, so what we have here is we have a quadratic. So let's visualize it. Maybe we have a row vector A transpose times a matrix W times a column vector B. And all of this gives us a scalar J. Okay, so we can rewrite this matrix vector expression with two sums, J and K. So here J is indexing across A, and K is indexing down the B vector. And of course, that means that J is indexing down the rows of W and K is indexing across the columns of W. And so this is what we get in terms of the summations of our cost J. Is everybody good with that? Okay. So what we would like to do is we'd like to take the gradient. We'd like to compute the gradient, but just to try to simplify it, let's just imagine that our goal is to compute the gradient, or let's say the J prime and K prime entry of the gradient. So I made some small changes to the slides just this afternoon. So if what you're looking at doesn't have the primes, I just put the primes in there in order to try to prevent confusion between this J and K and this J and K. I don't want them to be the same just because sometimes that causes some confusion. So this J and K are being used to index the sum, and this is another specific J prime and K prime. So we want to basically compute this element of this gradient, which in other words, by definition, means I want to compute dj d w j prime k prime. And so if you apply this derivative to this expression, due to linearity, the derivative can move into the inside part. And then you can notice that if we're differentiating in respect to j prime and k prime, that the only way you'll get something non-zero is when j in the sum is j prime and k in the sum is k prime. So all the other terms in that sum go away. The only terms you care about are when this is j prime and k prime. And in that case, you take the derivative of this with respect to w, and that simply gives you the a and the b components. And since we're looking at j prime and k prime, you get a, j prime, b, k prime. Okay, so does that make sense, what we just did there? Are there any questions on this? Don't be shy if you have a question. Okay, so, okay, and what's interesting is this is actually quite unusual that this gradient of this function doesn't actually depend on on the W we're looking at. This is just a constant that holds for all W. This doesn't usually work out this way, but in this simple case, it does. That's because this is actually a linear function with respect to W. In any case, this is what we get for the J prime and K prime entries of this gradient matrix. So now, how do we build back the entire matrix from there? Well, it turns out that when we look at the entire matrix, it's just A, B transpose. So if it's, I don't know if it's not obvious in going from here to here, maybe you could instead go backwards and say, well, if this is the gradient here, what would the J prime row and K prime entry of that matrix be? Okay, so this is a matrix. This is a column vector times a row vector, which is an entire matrix. So what we're saying is, let's look at the J prime row and the K prime column of this. Well, if I'm looking at the J prime row, I could look from the left or the right. That's going to be this entry here, and the K prime column is going to take this entry here. So that's how you can sort of see how to go from here to here, but obviously you can go either way. Is that making sense? How we went from this expression to the full matrix one? Okay, this is basically just linear algebra, homework 0 type stuff. Okay, so now we have our gradient matrix. And so let's look at the linear approximation of our function at the reference point W naught. So we know, based on the formula we derived on the previous slide, we have J at any W is J at the reference plus This is the inner product. In this case, it's the trace of the gradient transpose the deviation from the reference. So that's just this expression. Okay, now we can do some simplification because we derived what this thing is. We can plug this in here. So this is AB transpose, that whole quantity transposed. And then when we look at, we can apply the transpose here to this. Remember, that means we have to swap the order and transpose the individual terms. So that gives us BA transpose. And now we can use this really nice property of the trace, that the trace of a product, BA, anytime you have that, you can swap the order of B and A, this trace of AB. As you know, you can't usually do this with matrices. Like if the trace wasn't there, you can't swap the order and say it's the same thing. But when the trace is there, you can. So that's what's cool about the trace. Okay, so we're going to use this trick to think of this as the second, and this is the first term, and we're going to swap their order, which gives us this times this. And then we're going to realize that this is a row, matrix, column. This is a scalar here. So the trace of a scalar, remember the trace is the sum of the diagonal elements in a matrix? But this matrix is just a scalar. So the trace is doing nothing for us. We can leave out the trace, and we have the same expression. And finally, we can notice that there's an A transpose minus W naught B here. That will cancel with the first one, and will just give us this term. So after all this work, we found that the linear approximation of this function is the function itself. Okay, so that's maybe not surprising. If we realize that this was just linear in the first place, and we do a linear approximation, there's nothing to approximate, it's exactly linear, we lose nothing from the approximation. Okay, so really the value in this is just going through the exercise and playing with transpose and trace and so on. Because this stuff definitely comes up a lot, it's very useful. Yes?
About the second step, maybe I wasn't paying enough attention the last class, in the differentiation part. The step at the top of the page.
From here to here?
Yeah, that one, yeah.
Okay.
So there, what exactly is propagating J and K from 1 to whatever the order of the matrix is? Usually we have a summation or some kind of product term, right? But in this case, we don't really have anything to propagate J from 1 to the order, right? So how do we exactly understand that each element of the W matrix is being differentiated by its respective element?
I don't understand your question exactly, but so this is a matrix, and this is just, let's say, looking at one specific element in the matrix.
Then in that case, all the other elements except for that specific element have to be 0, right?
No. You have a whole matrix and you're just looking at one. When you're looking at one, doesn't mean you're changing the others.
No, but according to, we got a matrix at the end, that means we have differentiation in each and every element with their specific element, correct?
Yep. Mm-hmm.
So that's not my question. Is that we have a J and we have a K. Usually we have a summation term or some kind of product term to sort of propagate J from 1 to n. But here we don't really have any kind of summation or product term, right? So how is the J getting propagated from 1 to n?
I don't know what you mean by propagated.
Maybe the word is wrong here, but then what I'm trying to say is that J sort of moves from 1 to n all the time. We have a summation term or we have some kind of sigma or a pi term.
So this is like, we have a whole matrix here, right? I have a matrix. I want to look at one entry of a matrix. So the way I do that is I just determine which indices I want to look at. I'm going to call them J prime and K prime. And now when I look at that entry, I have a scalar. And that's what this is. Yeah. So the reason we're doing this, the reason we're looking at scalars is because we know how to do calculus with scalars. It is possible to do calculus with vectors and matrices, but that's much more complicated, and I don't assume you guys know how to do that. So I'm bringing things, we're starting here in the case of vectors and matrices. We're converting it to scalars and sums, then we're looking at the gradient at a particular entry of this matrix, which allows us to do the scalar derivative. We can solve that using techniques we know. And now we need to go back to the world of vectors and matrices. And so this holds true. I don't know if this is what you're missing. This is for any j prime and k prime that is a valid index. Because we didn't make any specific assumptions on what those were in deriving this. And now that we know that this holds for any values, we can basically go back to the world of vectors and matrices, and we can expand this into this full matrix. So it's like we derived the form of this little term here, and then we realize, oh, that's just what happens at that location, but that's, a similar thing happens elsewhere, and when we expand back outward, we get this outer product here, A, B transpose. I don't know if that clarified. Okay, any other questions here? Okay, all right, so let's talk about how we do some of this in Python. And this is super important, and also, let me just warn you, Lab 6, students usually say is like the hardest lab of the semester. And it's difficult mainly because of some of this, what we call Python broadcasting, which I'm going to talk about on this page. So please pay attention. Okay, so this is the function we want to evaluate in Python. So how do we do this? So first of all, in Python, when we do matrix vector multiplication like W times B, we can do this with what's called the dot function. So this is a NumPy thing. So W as a NumPy matrix has this dot function associated with it that allows you with W dot B to compute this guy here. So that is a column vector. It's just a vector. So kind of an important thing to realize that in Python or in NumPy, when you have a one-dimensional quantity, it's neither a row nor a column. To think about whether something is a row or a column, you have to be thinking already in 2 dimensions. So in NumPy, when you're working with a one-dimensional quantity, a vector, it's just basically like a list of numbers. You don't have the concept of row or column. So here you end up getting, when you do this, you end up getting a vector, which is neither a row or a column, it's just a vector. And you can basically take this A transpose times that vector. That's an inner product or a dot product. That's where the name comes from. So once you compute this, then to compute the whole thing, you do A dot this. Okay, so this is how we can compute this. Any questions on that? Okay. So the next one is where we have to start talking about Python broadcasting. So here, we want to compute a matrix that is what we call an outer product of this column vector A and a row vector B transpose. So again, let me draw a little picture here. This is what we want to compute. This thing is a full matrix. Okay, so if you want to think about this in terms of the jth row and kth column, the jth row, kth column of this ends up being AJ times BK. Okay, this is what we got from the previous page. So if we were doing this with for loops, you could build a pair of for loops over J and K. And when you're at index J and K in your for loop, you could fill in one element of the gradient vector to be this. So that would be pretty straightforward. But for loops are incredibly slow. So we don't want to use for loops unless we absolutely have to. So we'd like to do this with some of the built-in numerical processing capability of NumPy. And so we'd like to do this just in one line, no for loops. And the way that you do this is you end up sort of embedding this one-dimensional A into a two-dimensional size object in NumPy. And you can do this like this. A, and then in square brackets, colon, comma, none. So this grows it from 1-dimensional to 2, but what it does is it's saying this is a 2-dimensional quantity, but really there are no, there's just one column. There's not like a bunch of columns. So it takes a 1-dimensional list and it creates a column vector from it. Now if you want to do this, make a row vector, then you do it this way. B, none, comma, colon. This makes a 2-dimensional quantity that's really just a 1-dimensional row vector. Okay, so these are examples of Python broadcasting, is this stuff. And this is what we're going to use. So we have column A, row B, and then we can just do this multiplication with the star command, or star operator. And the star operator stretches the quantities as needed. Okay, so it knows that it can take this guy here and multiply by this guy here. Here's an example where instead of the multiplication, we do this with addition. Okay, so let's say that we start with a vector A, which is 0, 10, 20, 30. So what we do is the first thing is we expand that to, so it starts out 4 by 1, or yeah, we basically make it a 4 by 1 quantity. And then let's say B is 1, 2, 3. We do this, and now it's 1 by 3 quantity like this. And when you use the plus, so this is a plus operation here, essentially what is happening under the hood is you're expanding this into this, you're expanding both this and this so that they have the same dimensions. And then you're doing the plus. So that expansion, or they call it stretching, is basically like adding those extra columns here. This is for what happens with the plus, and adding those extra rows. And then when you add them, you can see you get these zeros plus 1, 2, 3 gives you 1, 2, 3. Right here, 10s plus 1, 2, 3 gives you 11, 12, 13, and so on. Okay, so this is an example of how broadcasting works with the plus sign. It works just a tiny bit different with the multiplication sign. But this link here, remember green is a link. If you click on this, it takes you to the NumPy description of all the broadcasting stuff. So if you ever have questions, you wonder what exactly is happening when I do this, click on this link and it will tell you. If you want to know, exactly what does this none mean, click on that link. It'll tell you. Yeah.
So what does it mean the asterisk stretches as needed?
So in the way that this addition, in order to add things, they need to be of the same size, right?
So asterisk is not multiplication?
Yeah, it is. So this example down here is addition. But what we're doing up in this here is multiplication. So I took this from the broadcasting manual. They didn't have a picture of the star, of the multiplication. They had a picture of addition, so I plopped that in. But, it also shows you that there's different ways broadcasting happens. Like another way broadcasting happens is if you have like a matrix and a scalar, and you do that scalar times the matrix, then NumPy is smart enough to know that scalar is going to be applied to every value in the matrix. That's another form of broadcasting. Or if you have a scalar plus a matrix, NumPy is smart enough to know to add that scalar to every element of the matrix. That's another example of broadcasting. So broadcasting is kind of like a set of routines where you can operate on things that don't have the same size. Using rules that make sense.
Is there any specific reason that we don't use np.matrix?
np.matrix.
np.matrix. That's a command that we don't don't have to do all the non stuff.
So I don't know, maybe that's another way of doing it, but you specify the dimensions then?
No,
Or-
you just like we know here we want A as a vector. But
We-
if you pass A as NP dot matrix, then it will be a vector, so we don't need to change it.
But like, for example, that's not enough to know that A and B, because like there's two different things I could do. I could also be computing A transpose B,
Yeah.
right? And so without telling it which one I want to do, it doesn't have enough information. So that's why I'm thinking the matrix command you must also tell it the dimensions you want this thing to be when it's done. I don't know.
I think that's the problem of dots too. Like if you use MP dot mat move, which is for matrix multiplication, that would be solved.
Okay, so this Python broadcasting is a very standard thing to do. So that's in part why I'm teaching it to you. There may be some other methods too. Usually in NumPy, there's like various ways to do the same thing. So this is just, pretty standard approach. And I think it's relatively straightforward. Like once you get the hang of it, you can turn this into a column vector, you can turn this into a row vector, and then just do the star like you would do in MATLAB. Right, so, but yes, there's probably other ways to do it as well. Okay, yeah.
Just wanted to clarify, would broadcasting be faster than a normal matrix multiplication?
So broadcasting is allowing us to do this correctly. I mean, basically, it is allowing us to do a matrix multiplication or a column times row multiplication. So it's definitely faster than nested for loops. There's probably other ways to do it that are similar speed, but this is one way to do it. Okay. All right. Any other questions? Okay, so you'll get some practice with this stuff on the next lab. But basically, as you can see here, we've made a function. It takes in W, A, and B. It first computes the cost, J. Then it computes the gradient, AB transpose. And it does each in one line, no loops. And then here, for the rest of this example, we're just creating some random quantities, W, A, B. We're creating them zero mean, unit variance Gaussian entries. And then we're just evaluating that and printing out the J and the J grad that results. Okay. All right, so we have all the ingredients now to talk about gradient descent, which is going to be the algorithm that we use to minimize our cost function. So we have to first talk about a few preliminary things. So as we've seen many times throughout the course, we know that at the minimum, under some conditions, which I'll talk about in a second, the minimum is this, this nice thing happens where the gradient equals 0. And you can see that here. This is a one-dimensional function, where at the minimum, the gradient equals 0. Here is a two-dimensional function we've seen before. This is the minimum here. And as you can see, the length of the arrows equals 0 here. But there's other points where you get a 0 gradient. So for example, at this maximum, you can see that the slope equals 0. Same thing with this maximum. But that's not the only place that happens. It also happens at saddle points. So these are examples of saddle points. So at that red dot there, the slope in all directions is 0. And saddle points are sort of like, they're neither minima nor maxima. The curvature is positive in one direction and negative in the other. So, and there's actually different kinds of saddle points. This is one type of saddle point. This is another type of saddle point. But in either case, the slope is 0 at that saddle point. So we have to be a little bit careful when we say we want to, use this idea to find a minimum. We have to realize that if we're not careful, we could instead be finding a maximum, or we could be finding a saddle point. Okay, and then the other thing is, in a lot of problems, we can't analytically solve that equation. We need to program it somehow with an algorithm, and that's essentially what we're going to talk about now. So gradient descent is the algorithm that we use to do this. So our goal is to find the minimizer of our cost function j. Sometimes it's called the objective or the loss function. In other words, we want to find the w, we'll call it w hat, that is the minimizer of j. We are going to assume that there are no constraints on w. Like, for example, constraints could be if someone says all the entries of w have to be positive. That would be an example of a constrained optimization problem. We are going to assume that there's no constraints on w. This is an unconstrained problem. We're also going to assume that the gradient exists, or in other words, that j is differentiable. This is not always the case because, as we saw, like lasso, that lasso cost was an example where the gradient doesn't exist at the origin. But for now, we're going to assume that that exists when we talk about gradient descent. So with those preliminaries, this is the algorithm. Basically, you choose an initial point, we'll call it W0, and then you iterate this step until convergence. So for any k, the next W is you start with WK, and then you take a negative gradient times a small positive number, alpha k. That little number, alpha k, is called the step size or the learning rate. It tells you how far you move. It's something that multiplies the gradient. So how far you move is also proportional to the norm of the gradient. But this is an additional factor above the norm of the gradient that tells you how far you move. And in words, you could say, take small downhill steps until you reach the bottom. That's essentially what this is doing. So here's a picture when you have two parameters that you're adjusting. Maybe you start here. These circles are the cost contours. So in other words, every point along this, that's actually an ellipse, every point along this ellipse has identical cost. All these points have identical cost, but it's smaller and so on. So let's say we start here. The gradient is going to be always perpendicular to the cost contour at that point. So we move perpendicularly in this direction. Maybe we move that far. And then at the next iteration, we reevaluate the gradient. Now it's turned a little bit to the left, and we move a little bit more. And then now we're here. We again move perpendicular and so on. As you can see, we're curving in, and we're eventually reaching the solution. The steps that we're taking are getting smaller and smaller because in part because the surface is getting flatter and flatter. So the norm of this term is getting smaller and smaller. But you can also, if you want, use an alpha k that varies with the iterations. It's a possibility. So this is gradient descent. This is sort of like the basic scheme that we're going to use to minimize our cost functions. All right. So any questions on this? Very important idea. Yes.
What do you mean by convergence?
Convergence basically means you get closer and closer to the solution. So we're not going to be talking about, well, let's see. So we'll do a little bit of convergence analysis, but we're not going to do like a very rigorous definition of what we mean by convergence in the way that you would do in a math course.
So how do you know that you have reached the right solution?
How do we know that what?
I mean, you're saying that we reach convergence means we reach the minimum, right?
Yeah, that's the goal. Is we hope to get closer and closer to the minima. Eventually, maybe after an infinite number of iterations, we would get there.
So how is it better than finding a saddle point?
It's possible to find a saddle point this way. So let me show you an example. So imagine that I started, imagine that I started exactly on the line that, takes me right down, and then I would basically get stuck there. Right? If I was coming exactly on that side. If I was started a little bit to the side, I would basically, I'd get close, and then I would curve down this way. So that's a very good point. It is possible to get trapped at a saddle point using this method, but I would say it's very unlikely, because if you're just a tiny bit off the trajectory that will trap you, you won't hit it. You'll actually converge to a minimum. But it does raise another point that that it is possible, if you have multiple local minima, to converge to one you're not interested in. Maybe there's a good local minima and another that's not as good. If you start close to the not as good one, you will converge there instead of the good one. So I think that there's a future slide where we discuss that. But yeah, those are definitely issues with this approach. And one of the ways that we can feel better about this is if we have what's called a convex cost function, then we don't run into this problem. Essentially, there's going to be all the local minima are going to be global minima. There may be more than one, but they're all equally good. We'll also talk about that a little bit later. Yes?
Like to move from one rank to another, you're just changing the weight, right?
Yeah, the weights in this picture are this pair of numbers. So as we move around the space, we're changing the values of the numbers.
Okay.
What these ellipses show is they show the value of the cost j. So like along this outer one, these are the set of w for which the cost is all identical. Those are equal cost contours.
Okay, so what do you change to go from one rank to another?
Well, we're first of all, we're moving w, and we're moving it according to this rule. So we're looking at the gradient, which is the downhill direction at that point. And we're scaling that by some value, and then we're moving relative to our previous guess by that amount. So let's say we start here. The gradient is pointing in this direction, but I'm going to make sure I use a small enough step size that I'm not like landing all the way over here. Because if I had a very large step size, you can see I could move in the direction of the gradient, but maybe end up here, which is actually worse, higher cost than when I started. And then maybe I could move here and have a higher cost again, and so on, and I would actually not converge. I would go off to infinity. We don't want that to happen. So we'll show on the next page, we'll argue that when this is small enough, this should bring us closer to the solution. The cost should decrease, or at least not increase. Okay. All right, yes?
So, this superscript W0, it is actually like, here it is like a pair of W and
Yeah, so this bold-faced W, like always, is a vector for us. So that's going to be a vector of all our parameters. You can do this with matrices too. It could be a matrix, but we're just going to think about it as a vector now. The superscript does not mean to the power of. It means it's just a way of denoting the iteration of the algorithm.
And since there are no constraints on W, like,
In this problem, yeah, this is unconstrained.
so does that mean like, I mean, we could start at very high W value?
Yeah, so usually you initialize randomly in a lot of these applications. You just generate like a zero mean Gaussian initial value. And then you start from there, and it might be really bad, but you start from there and you make it better using this iteration. Okay? All right. Good questions. Yeah.
That's worth asking, is there a way to pick a W not that like will never converge?
Well, maybe we'll answer that in the next slide. Yeah. What's going to be key is when this guy is small enough. It's not so much about the initial value, it's about how you move during the optimization. Okay. you have a question?
Yeah, if we were to start at the minimum, gradient at that point would be 0.
That's right. And you would not move at all because this part would always be 0. So you would just stay.
So how would we define here at the saddle?
Yeah, so this is also a problem. If you started exactly on a saddle and the gradient is 0 there, you would never leave the saddle. You'd be trapped. So again, it is potentially possible to have a disastrous consequence in converging to a saddle or starting in a saddle and never leaving, but in practice, it's quite rare because due to things like numerical precision and so on, it's difficult, unless there's some problems where maybe like structurally the origin is a saddle. That definitely occurs. Part of the reason we choose things randomly is that when you choose that initialization randomly, there's like essentially probability 0 that your random initialization will be at a saddle. But choosing like W0 equals the origin 0 is a bit dangerous because it could be that for your problem that's a saddle point or a local maximum or something, and then you would actually be stuck there. So that's part of why we choose this randomly. Okay, so let's talk a little bit more about why this works when alpha is small. And once again, we're going to use our Taylor series expansion. So this is the cost at any point W, and as a reference, we're going to use WK. So it's sort of like imagine that we've been running this algorithm and now we're at WK. That's going to be our reference point. We want to know what happens relative to that reference point for any W. So this is just the Taylor expansion that we derived, or we discussed this last Wednesday. And now we're going to look specifically at W as the next gradient descent iteration. So we're looking at, this is our reference, and this is the next point. So what can we say about the cost at the next point relative to the cost at the reference? Well, we're going to plug in for W, we're going to plug in WK plus 1, here WK plus 1, and so we get this expression. So all we've done is put in those points. And now, go further and remember that for this gradient descent update, the new point minus the old point is the negative gradient. Right? That follows directly. This minus this is this. So we know this is true, and we can actually plug that expression in for here and here. So we can replace those with this. Okay, so when we plug this in here, we're going to get a minus alpha, and then gradient, this will become the gradient. On the other hand, when we plug this into here, the negative sign doesn't matter because of this norm squared. Remember, the norm squared is the sum of the terms squared, and that squaring basically kills the sign. Okay, but we do have this alpha k here. We can pull the alpha k out of the norm, and because of the squared term, it manifests as alpha k squared, and then we have the norm of the vector quantity. Okay, so basically, this is what we have. And now we're almost done. Let's realize that this vector transpose itself is just the Euclidean norm squared. So here we have this term and this term are actually identical. And we've done one other little thing is we've pulled this, actually we pulled this norm out of this order expression. And we do that mainly just for conceptual reasons. So now we have this term order alpha k squared, and we notice that that is one scaling on this term, and then we're adding minus alpha k times that same norm. So basically, altogether, we have the new cost equals the old cost minus alpha k plus order alpha k squared times this norm. And what we would really like to happen when we're running gradient descent is we would like that the new cost is less than the old cost, right? That means we're making progress. At least it should never be greater, because if the new cost is greater than the old cost, we've made negative progress and something is wrong. So, so when exactly do we make progress then? Well, this norm squared is always positive. So really we have to look at what's multiplying it. So in front of that norm squared, we have this order term, order alpha squared minus alpha. Remember that what we mean by this order alpha squared is that for small enough alpha k, that this term is upper bounded by some constant c times alpha k squared. We don't exactly know what that number c is, but there is a number that exists. And so finally, when you look at this, you have really two different terms multiplying this norm squared. You have c times alpha k squared and minus alpha k. So here's the key point. If you make alpha k sufficiently small, essentially this term will overwhelm this term, and that means that this whole thing will become negative, or at least never positive. Okay? The reason why that works is, remember, when alpha k is very small and you square it, it's even more small, right? When it's less than 1 and you square it, it's even more or less than 1. So that's the idea. No matter what c is, you can always find a value of alpha k such that the magnitude of this is larger than the magnitude of this. So that's why we can say, if we make our step size sufficiently small, we will make progress in the sense that the new cost will be no larger than the old cost. In most cases, it will be smaller, but we have to acknowledge that, for example, if you start at a minimum, you can't make it smaller. In that case, it would be equal, but usually when you're converging, it's actually getting smaller and smaller and smaller. Okay, so again, we can always make alpha k small enough so that this term is smaller than this term, no matter what this constant c is. And in that case, this middle term, which is the progress term, will dominate this term, which is like the anti-progress term, negative term and the positive term. Okay, so this is how we can understand why gradient descent works, at least when alpha k is small enough. Okay, so this is sort of the extent to which we'll talk about convergence of this algorithm. You see that the cost is getting lower and lower when alpha k is small enough. Okay, any questions about this? Yes?
So if you don't know the C, you can never really know the best alpha k.
That's true, although we'll develop an algorithm that can figure it out no matter what. Yeah, it's a good point though. Like if it's not really clear how, it's not exactly obvious how to choose alpha k. So what people do is trial and error. They try one, they look at how the convergence is going. It's not going well, they try another one. But there are a class of auto-tuning algorithms that basically can choose this alpha k as the algorithm is running. A lot of them will just keep decreasing it, but sometimes they can increase it as well. And we'll talk about one. Okay. Great. Any questions on this analysis? Is this making sense? Okay. All right. So coming back to this idea of when this works or fails, we acknowledge that if you start right at a global maximum where the gradient is 0, gradient descent will not move you at all. That's a problem. But maybe if you started over here, you can see that gradient descent will take you down to here, which is what we call a local minimum, which is not as good as our global minimum, which has a lower value. So, there are cases where the cost function has only global minima. There's cases where it has local and global minima. It really depends on the cost function. But the thing we have to remember is that gradient descent only guarantees convergence to a local minimum, or if you started exactly at at a saddle point or started at a maximum, then it just doesn't even move at all. So one of the things we said you can feel better about is if you have a convex function, which we'll talk about, maybe not today, maybe the next lecture, is that it avoids this problem because any local minimum is a global minimum, and you don't have any maxima to worry about, don't have any saddles to worry about. So this works just as we would hope. Okay, but we'll talk about those convex functions a little bit later. Okay, so with all of that, we're ready to start looking at how we can optimize our cross-entropy loss, which is the loss that we saw in logistic regression. So previously we used some built-in scikit-learn solver to do this, but now we can try to do this ourselves with the tools that we learned about. So essentially, we need kind of an efficient way of attacking problems like this. So a lot of the problems we see in machine learning have this form, where you have a sum over the training samples, and then for every training sample, you have a cost for that training sample. And moreover, because our logistic regression, the regression part is sort of reminiscent of, it's a linear method. Essentially, it was reminiscent of even like the least squares technique we learned originally, in that you have features, and maybe here we have like an intercept term that are linearly multiplying this W to get these scores as an intermediate quantity. And then the scores are being put into some nonlinear function to get our cost. So you can think of this as a two-step process. The first step is you take your weights, you multiply them by, these are the rows of the A matrix, to get what we'll call the Z vector. And then as a second term, we have this cost is some function of that Z vector, we'll call it F. And that F has a form of a sum here times functions that work on the individual elements of Z. So there's two-step, linear transformation followed by what's called a separable function. So F is separable in that you can decompose it as a sum of primitive functions working on the indices in Z. Okay, so in statistics, they call this the generalized linear model. There's tons and tons of applications of this. One application that we're seeing now is binary logistic regression. There's many other ones as well. So in our case, what is this function f, or what are the functions fi? Well, this is just the function fi, and it operates directly on zi. So this is the function fi. Okay, so overall, you can say j is a function of omega is like you go from omega, sorry, not omega, w. J is a function of w is like going from w to z and then putting z in f. So it's a two-step process. And with this two-step process is just a way of sort of organizing the computations and helping us attack them in sort of a straightforward manner. Because without this, it looks kind of overwhelming. We have all this different stuff going on. But if we can separate it like this, we can make sense of it. Okay, so once we have this two-step process from W to Z and then from Z to F, we can compute our gradients of F with respect to W, or the same as J with respect to W, using what's called the multivariable chain rule, which is something we'll use a lot for the rest of the term. So the multivariable chain rule says df dwj is sum over all these intermediate variables I, df dzi times dzi dwj. Maybe I could draw a little kind of computation graph here. We have f, which is a function of all these zi's, And then all those zi's are a function of these wj's. Okay, so this is the transformation from the w's to the zi's, and then from the zi's to f. And what the multivariable chain rule says is that if you want to take a specific one of these, I'll draw it in red, and f, and you want to say, how do I compute the gradient from this wj to f? You basically have to look at all the different connections between that w and f. You can see these are all the different connections. Let me put them in red. So this summation over I is exactly that. It's acknowledging that this particular wj is connected to f through all these multiple paths. And for each path, you have to compute the gradients, and then you have to add those paths. Okay, so that's the idea. And this, when we get to neural networks, this will be the foundation of the backpropagation rule that we use to train all the weights in the neural network. Okay, but for here, this is sort of the simplest incarnation that we have. And essentially, we just need to compute these quantities. Is everybody with me so far on this idea? So I believe this is something you guys all learned in calculus some years ago. And it's probably something that you actually, if I just gave you a problem, like, differentiate this with respect to zi, you end up using, you end up using this almost unconsciously. Maybe you don't often write it that way, but you guys know how to do this. Okay. All right, so everybody good with this multivariable chain rule? All right, let's see how we can use this then. So let's first look at this first term, df dzi. So then we just look at this. This is the whole function f as a function of zi. So how do I take the derivative of this with respect to zi? Well, I move this through the sum. I realize that there's only one of the terms in the sum has the I that matches this. And then I just take the partial derivative of this thing with respect to zi. So with the log, that means we get 1 over 1 plus e to the zi. And then chain rule, we have to multiply that by the derivative of this with respect to zi, which is e to the zi. So that's the first part from the log. This is the second part from the chain rule. And then we take the derivative of this with respect to zi. It's minus yi. Everybody okay with this step? Okay. And then finally, we can move this up to here, and we can basically multiply top and bottom by e to the minus zi, which will cancel this, turn this into e minus zi, and turn this into 1. In doing that, we only have one exponential to evaluate instead of 2. Okay, so that's the first term here. The second term, dzi dwj, for that we have to look at this term here. So actually we want to look at this one over here. So we can do this by writing zi as a sum over j, aij wj. Right? I'm just looking at the ith term in here. The ith zi is the ith row of A times W, which I can write this way using a summation. So given this, how do we do this? dzi dwj. It's pretty easy, right? You just move this through here. You then take the derivative with respect to wj, and you get aij. Okay, so once you have those two things, you plug them into this sum, and you have the term we'd like. Okay, so we can go through some more details about how we implement this next time, but this is basically the math behind it. After this, it's just looking at implementation. All right. If you have any questions, ask me after class, and otherwise I'll see you guys on Wednesday.